Hi guys, it's Andre from High Performance Academy. Welcome along to today's webinar where we're going to be having an introductory look at diesel engine tuning. Now, particularly for any tuners out there who are more familiar with gasoline engine tuning, when it comes to diesel engines, the technology or the approach to tuning, I should really say, is dramatically different. In fact, particularly when it comes to aspects such as the fuel delivery, as we'll see a little bit into this webinar, the way a diesel engine responds is almost exactly the opposite to how a gasoline engine performs. So it's going to be a bit of a learning curve for anyone coming from that gasoline tuning background to jump in and start learning how to tune common rail diesel engines. Now, the reason we are running this webinar is over the years we have seen the common rail diesel engine market sort of grow a lot, and we're seeing an adoption with those engines for motorsport use, and we are also seeing a lot of the vehicles fitted with these late model common rail turbo diesel engines being used by tradespeople. And when it comes to modifying these engines electronically, there's often really large gains to be had in both torque and power. Sometimes also this comes along with an improvement in fuel economy. So for tradespeople who aren't necessarily interested in maybe cutting a faster lap time around their home racetrack, there are still really big gains to be had, and also really useful if it comes to towing loads. So regardless whether you are looking at an actual motorsport application or you're interested in improving the performance of a road going vehicle, there are some really good options on the market now for doing exactly that. And this comes down to the support we're now seeing in the aftermarket, with some standalone aftermarket ECUs being produced for common rail diesel engines, and also we're seeing support from a lot of the commercial software manufacturers who produce software for us to reflash factory ECUs, allowing us to reflash the ECUs fitted to common rail diesel engines. So in this webinar we are going to have an introductory look at the operation of a common rail diesel engine. We're going to investigate the operating principle of the diesel engine, and then we're going to have a look at some of the concepts that we'll be talking about being applied here on our Toyota Hilux, which is fitted with a 1KD 3 litre 4-cylinder diesel turbo engine. And we're going to be demonstrating those principles today using a MoTeC M150 diesel beta package. Now, I'll just mention that right now, beginning of 2018, this is still in beta and it is not available for public release, but that will be coming in the not too distant future. To help us with some of today's webinar, we are also going to be using a few slides provided by MoTeC as part of their diesel training course, and I would like to thank MoTeC for those slides, as well as Pete Swinney who developed that course. Okay, so let's start at the very start with the operating principles of the diesel engine. I'm not going to get too deep into this. We'll just look at some of the core principles here, and really the main one for those coming across from gasoline engine tuning is that obviously the diesel engine does not include a spark plug. There is no ignition system. Instead, what it relies on is auto ignition of the fuel. So the way that this works is that it relies on the temperature being built up inside the combustion chamber during the compression stroke. And as a point here, we normally find that diesel engines have very, very high compression ratios compared to gasoline engines. It's not uncommon to have a compression ratio of 18:1, 20:1 or greater, even though we will be dealing often with a turbocharged engine. So as the air inside the cylinder is heated up during the compression stroke, at this point no fuel has been added. Now the fuel is injected directly into the engine near the top of the stroke. So often we'll find with a diesel engine that the fuel injector is placed in a location that we may normally see a spark plug on a gasoline engine, and what it's going to do is inject that fuel down into a bowl that's on the top of the piston. So the top of the piston actually forms our combustion chamber in a diesel engine. So what happens is, as that fuel is injected, it becomes superheated due to the temperature inside the combustion chamber, and the fuel will begin to burn. Now the process from here is actually quite similar to what we see in a gasoline engine. The fuel is injected and burns, and we see a rise in the pressure inside the combustion chamber as a result of the combustion process. So again, just like a gasoline engine. There are some differences though. What we find is that with a diesel engine, as we'll see shortly, the burn rate is quite a lot faster than in a gasoline engine. And what we'll find is that the cylinder pressure rises, and it's the cylinder pressure, just like in a gasoline engine, acting on the top of the piston that provides the torque at the crankshaft. Okay, so we'll just have a quick look at a slide here. So this demonstrates the four-stroke principle really being applied to a diesel engine. So again, very, very similar to a gasoline engine. We've got our intake stroke here. Now again, during the intake stroke, there is no fuel being added. So no fuel is injected through the intake port, as we'd see with a port-injected gasoline engine. We've got our compression stroke, which is our next stroke. So the high compression ratio of the diesel engine causes the air inside the combustion chamber or inside the cylinder to become superheated. When we get our piston right up near the top of the stroke, this is where the injection occurs. So we can see again, as I just mentioned, our injector is fitted to the top of the cylinder head, pointing directly down at the bowl inside the piston. As the fuel is injected, it does begin to combust, as I've already said, and that produces pressure in the cylinder. That's where we have our power stroke occur, and then finally we move on to the exhaust stroke, again just like we'd see with a conventional gasoline engine. So really the key difference there is that we're relying on the heat inside the combustion chamber to superheat that fuel and cause it to ignite. The other point there is that the fuel is injected very close to top dead center. So what we'll do now is we'll just have a quick look at another slide. This is what happens once that fuel is injected. So we get the fuel initially injected, and to start with, nothing happens. The fuel doesn't initially combust. What we find though is as the fuel absorbs heat from the combustion chamber, it becomes superheated and it will expand. It reaches the ignition point and it begins to burn. So there is a delay, which is really important to understand, between the fuel initially being injected, becoming superheated, and then the combustion process actually starting. So what we find then is each of the fuel droplets will consume the oxygen surrounding it until all of the fuel is burned. Now if we get into a situation which we're going to demonstrate a little bit later in the webinar, where we don't have enough oxygen in the cylinder, then we're going to end up with one of the more common scenarios with diesel, which is where we end up with high particulate matter in the exhaust, or in other words smoke, and that's what's happening over here. So you've probably all heard the term rolling coal, and we've all seen diesel engines, particularly in tractor pull or drag racing applications, which are blowing clouds of black smoke. So that's that particulate matter that we're seeing there. So that's the process that we go through here. And one of the really key takeaways or differences between a gasoline and a diesel engine is that with diesel engines, we're always going to be working with a lambda value that is leaner than stoichiometric. With a gasoline engine, it's almost always the opposite way. We're always going to be on the rich side of lambda 1. With a diesel engine, we're going to be operating on the lean side of lambda 1. So again, this is a concept that's really foreign and really difficult to get your head around if you are not used to diesel engine tuning. Now, don't worry too much about these concepts. We are going to be demonstrating them on the dyno, so you're going to get a better idea of them really shortly. There are a few more things that I wanted to talk about here though before we get into this. One of the aspects is throttle bodies. Now obviously if we're used to dealing with gasoline engines, our engines always have a throttle body. We use our throttle body to control the airflow into the engine, and this is our main way of controlling the engine torque and engine power level. In diesel engines it's very different to that. We don't actually require a throttle body in order to we don't need a throttle body in order to modulate the engine power. What we're going to do instead is modulate the engine power by adjusting the fuel delivery. So again, really different. The Throttle bodies, though, we will find, while they're not necessary to modulate the engine torque and engine power like we use in a gasoline engine, we will still find that common rail diesel engines will incorporate a throttle body, but it's for very different reasons. One of the main reasons they are there is to allow exhaust gas recirculation. So particularly at cruise, exhaust gas recirculation is a really important way of reducing the tailpipe emissions from a diesel engine, and particularly oxides of nitrogen. So it's important, in order for the exhaust gas recirculation to work, to create a slight low pressure area, so it's actually going to draw that exhaust gas back into the intake. So the electronic throttle body that we'll see supplied or fitted to these late model common rail diesel engines is going to close partially in order to create that low pressure area and allow the exhaust gas recirculation to work. The other area where the throttle body is often used is actually to close completely when the engine is shut off, and this allows the engine to be closed down or shut off quicker and more smoothly than if we didn't have a throttle body. The next aspect that I'm just going to touch on here, and this is going to differ a little bit depending on whether you are dealing with an aftermarket standalone ECU or reflashing a factory diesel engine ECU. And this comes down to how we measure the air mass or air charge entering the engine. So particularly in the aftermarket, when it comes to gasoline engine tuning, most aftermarket ECUs are going to calculate the mass airflow rather than measuring it directly with a mass airflow sensor, and they're going to do that by using a variety of approaches, but essentially what we're doing is looking at the manifold pressure, we're looking at all of the aspects of the air temperature, etc., and the volumetric efficiency of the engine. Thanks to the ideal gas law, then the mass of air entering the engine can be calculated. Now, when everything's working well, that calculation can be very, very effective. However, what we find is that with the majority of common rail diesel engines, they're often going to incorporate a VNT, or variable nozzle turbocharger. So this is a turbocharger with vanes in the exhaust side of the turbo, which can be open or closed in order to control the exhaust flow to the turbine wheel. The idea behind the VNT turbo is to provide good low RPM performance, good low RPM boost response, while still being able to open up and produce low exhaust back pressure at higher RPM and higher load. The problem with these VNT style turbos is that this also has an effect of varying the engine efficiency or airflow through the engine at a fixed point in the manifold pressure versus RPM table when the VNT nozzle position changes. So it makes it really difficult for us to use a conventional speed density tuning system on a diesel engine. Instead, a better solution is to use a mass airflow sensor where we are directly measuring the mass of air entering the engine, and we'll also find that this is generally the common approach from an OE manufacturer. Now, of course, if we are dealing with a diesel engine that doesn't incorporate a VNT turbo, then this becomes less of a problem and opens us up to a conventional speed density system for our tuning. Another aspect that's really problematic for us in the aftermarket is the injector calibration. With these injectors running at incredibly high fuel pressures, which is essential for the fuel to be able to be injected directly into the combustion chamber at the end of that compression stroke, what we find is that if we look at the flow across a set of factory injectors fitted to an engine, we can see really, really high variations from one injector to the next. So with factory injectors, depending on the exact injector manufacturer, it's not uncommon to see a discrepancy from one injector to the next of as much as 15% to 20%. Now, of course, that's going to be really challenging for us to get really good results if we're getting that sort of discrepancy. This is why we find that in the diesel tuning world, when we're looking at factory engines and factory injectors, when the injectors are replaced, these need to be coded to the ECU. So this is normally a QR code or a number that is on the injector. These are essentially, the injectors are batch tested and calibrated or checked by the manufacturer when they are produced, and this results in the QR code that's placed on the injector, and this gets coded to the factory ECU. So in a factory application, that's really nice and easy, it's nice and tidy. However, it is a bit of a problem for us in the aftermarket, and right now there is no easy solution. It's certainly something that I know MoTeC are currently working on, but right now it does present a bit of a problem for us, and we can expect to see some discrepancies from one cylinder to the next as a result of this error in the injector calibration. Okay, so what we're going to do is move on, and we're going to talk about some of our tuning considerations. So what we want to do here is look at how we're going to increase power, and generally what we're going to do here is to increase the power. This is going to primarily come by increasing the amount of fuel that we're delivering. So again, very different to gasoline engines. What we're going to do is provide more fuel, and this results understandably in a richer mixture. What this also does is it increases the combustion temperature, so there is a limit to what we can do here. We can't just go adding infinitely more fuel. It's going to create a lot more combustion temperature and exhaust gas temperature, which ultimately can be dangerous to our engine. Also at the same time, we're going to get back to that situation we were talking about earlier, where as we increase the fuel delivery, we're going to end up with smoke in the exhaust. We find that every engine obviously is slightly different, but a practical limit under wide open throttle full load operation is going to be somewhere around about 1.1 lambda. That's essentially the rich limit. It's as rich as we're going to be able to operate for smoke-free operation. Now the other trick here is that we can also increase the airflow, and what this will obviously do is then lean out the air-fuel ratio, but this then allows us, in a confusing twist, it also allows us to then add more fuel. So we're going to achieve more power because we're now burning more fuel and more air, but that leaning out, because we've added more air, allows us to achieve more power with smoke-free operation. So it becomes an iterative process here. This is why we're seeing the gains that we are seeing with turbocharged diesel engines. Now we also need to understand that there is an interaction between the fuel pressure in the common rail diesel system, the fuel mass that we are trying to provide, and also the injection timing. So whenabouts in the engine cycle we are injecting the fuel. So these all work together, and we need to really understand what is happening here. So if we look at a factory engine, the OEs obviously spend a huge amount of their energy optimizing the injection timing as well as the mass of fuel being delivered to give optimal results, but probably most importantly for them, they want to minimize their emissions. And what they're trying to do is select the fuel mass, the fuel pressure, and the injection timing to achieve a point called 50% burn, a little bit after top dead center, so after the piston has begun moving back down the cylinder on the power stroke. So this is similar, if you look at the way a gasoline engine works, this is similar to selecting our ignition timing. What we're trying to do is select our ignition timing in order to achieve peak cylinder pressure at a point in the engine cycle where we can take the maximum mechanical advantage from it. In turn, we're going to end up with maximum torque. So if you are reflashing a factory diesel ECU, then you're in luck because you are starting here with the factory setting. So you don't need to come up with an injection timing map from scratch. You don't need to generate your own injection timing map, and this is going to greatly speed up your process as well as ensuring an element of safety. If we get our injection timing too far advanced, then this can potentially damage our engine. If we are dealing with a standalone ECU like our MoTeC M150 here, then we do have a little bit more work to do, and it's always a good idea if we can get the factory timing map. Often with ECUs that provide reflashing options, we'll be able to get this through the reflashing software that's already available, or alternatively we may want to reverse engineer the timing map. So we've got a good safe starting point. Okay, so what we'll do is we'll just have a look here. If we jump across to my laptop screen, we're going to have a look here at what's actually happening inside the cylinder. So hopefully this will give you a little bit more of an understanding. So I'll just explain what we've got here. So the black line that we've got that I'm just drawing over at the moment, this is basically the pressure trace that we're going to see inside the cylinder. We're injecting no fuel, so if we're just cranking the engine over. So obviously as the piston rises to the top of the cylinder, there is that compression, so we see that pressure rise. As it moves away, the pressure drops away. So we've got our injection event occurring here, and at this point we're injecting 0.8 millisecond pulse width. Now that's being represented by this point here. Hopefully we can all see that. Now there is a delay, as I mentioned, there is a delay between the injection event occurring. The fuel then has to become heated to a point where the combustion process can begin. So that's what we're seeing here, this little yellow section of our graph. And we're seeing no pressure rise at this point. Once we get through the delay to combustion, we actually see the combustion occur, and we can see the pressure at this point climbs quite sharply. And again, just to reiterate, the combustion occurs much faster in a diesel engine than what we see in a petrol engine. What you could think of is essentially each of the individual fuel molecules creates its own flame front. So it's unlike a gasoline engine where we've got that flame front propagating out through the combustion chamber from our spark plug, burning the unburned fuel in the area ahead of it. Essentially all of our fuel molecules inside that combustion chamber are individually igniting and burning simultaneously. So we can see at this point there is also a point here that is labeled 50% burn or 50% heat release. So this is what we're trying to achieve there. I'll just show you another slide here as well, without getting too far ahead of ourselves. One of the problems, let's go back to this one, one of the problems with diesel engines, which has put a lot of people off over time, is the fact that the diesel engine is quite noisy. Particularly at idle, we get a lot of knocking from the engine, and one of the reasons for this is this very sharp pressure rise that we see when the combustion process occurs. And again, this is unlike the pressure rise we see in a gasoline engine. So this is what causes the knocking noise that we hear in a diesel engine. And one of the advances we've seen over the years is the adoption of pilot pulses. Now, I'm just going to cover this really briefly. We are going to cover this in detail in a completely separate webinar. So for now, you don't need to worry too much about this. What we've got here is a pilot pulse, which we can see occurring well before the main injection pulse. The main injection pulse in this case is exactly the same as what we looked at on the last slide. And what we see here is the pilot pulse, which is a short, very small injection of fuel, helps to sort of smooth out that sharp rise in pressure. And this is what we see with a pilot pulse addition. This helps reduce the noise from the diesel engine. Okay, now what I want to also mention here, actually just bear with me, I'll just make sure that I'm on the right slide here before I talk about this. Okay, actually let's just leave that slide for the moment. We'll just talk about this before we actually look at the slide, so you've got an understanding. We've talked about the interaction there of our fuel pressure, our injection timing, and also the fuel mass that we need to provide through the fuel injector. So we need to understand that if we increase only the fuel mass, what this means is that in order to provide more fuel mass, the injection pulse width needs to increase. Now what this means is that in turn the point where we get our 50% burn is also going to end up later in the engine cycle. So now that we've talked about that, let's jump back across to my laptop screen. I am sorry that this slide is blurry, but hopefully you'll be able to get the information we need. So at the top here, we're looking at exactly the same event that we looked at on our last slide. So what we've got here is an injection pulse width that is 0.8 milliseconds long. Now what we've done for our second point at the bottom here, we've retained the same injection angle. So we're starting the injection event 10 degrees before top dead center. This time, instead of an injection event that is 0.8 milliseconds long, our injection event is 1.4 milliseconds long. So what we can see is it basically pushes everything out to the right, and what we see is now our 50% burn happens much later in the engine cycle compared to what we saw in our initial example. So this is what happens if we only make one change, which is to provide more fuel mass. Okay, so if on the other hand we increase our fuel pressure, then what we find is that the same fuel mass can be delivered in less time. So again, if we only change one aspect, if we want to deliver the same fuel mass and we simply increase our fuel pressure, what's going to happen is that that's going to end up with our 50% burn point happening earlier in the engine cycle. So it's just understanding that interaction. Now if we alter the injection timing, then this also affects the point in the engine cycle where we achieve that 50% burn. So there's a few interactions there. It's not as simple as just adding more fuel. In particular, what we need to understand here is that if we are going to add more fuel, then what we want to do or going to need to do is to advance the timing. In other words, start the injection event earlier if we still want to achieve our 50% burn point at the optimal point in the engine cycle. Now this in turn can be problematic. If we advance the injection timing too early, this can be a really easy way to quickly damage our engine. What we need to be aware of is that if we're injecting too early in the engine cycle, then the fuel can end up impacting on the edge of the bowl and the piston, so the edge of the combustion chamber basically cast into our piston, and that can end up cracking the piston. So we do need to be very, very careful with this. So generally the approach that we want to actually take is to try and increase our fuel pressure as we increase our fuel mass being delivered. And what this will do is allow us to keep a very similar injection pulse width. What this means is then we don't need to change our injection timing. We're still going to end up with our 50% burn point occurring close to our optimal point, but we're not going to need to make wholesale changes to our injection timing in order to do that. Okay, so what we'll do now is we'll go through a bit of a practical demonstration here on our MoTeC M150 ECU. So what we're going to do first of all is demonstrate how the amount of fuel that we deliver affects the amount of power and torque that the engine produces. Let's have a really quick tour here of the M150 ECU. We'll jump across to my laptop here. So the screen that I'm on here, MoTeC have labelled as fuel mass nominal. Just to explain how this works, if we look here at this particular table, this table is our fuel mass limit main. So this is the maximum amount of fuel mass that will be delivered into the engine for each RPM breakpoint. And this is labelled, this is measured in milligrams. So for example, the maximum amount of fuel that will be delivered here at 2000 RPM is 137 milligrams. So this is our maximum amount of fuel. Now, we also have our fuel mass nominal table, and this defines what percentage of that maximum fuel is going to be delivered. So you'll notice here that the axis for this table as well is relative to our throttle position. So if we see a value of 100% in this table, what that means is that it's going to be delivering all of the maximum amount of fuel defined by our fuel mass limit main table. We'll talk a little bit about some modifiers or adjustments that can be made to that final fuel that's going to be delivered shortly. But what we'll do now is we're going to run our engine here at 2000 RPM, and what we're going to do is have a look at how the fuel being delivered affects our torque. So let's just get up and running, and we'll get to 2000 RPM. Okay, so what I'm going to do is I'm going to come to a light load area in our table. Let's just come up to 20% throttle. So this is probably the sort of area that we might be operating at a typical cruise. One of the important points to notice here, let's just get rid of that, is that our exhaust lambda on the screen here, hopefully you'll be able to see that, is currently sitting at 1.5 lambda. Again, for those of you coming from a gasoline tuning background, you're probably horrified. A gasoline engine's probably going to be unable to ignite the fuel and air charge if we were running that lean. Okay, so at the moment the number in this particular cell is 44%. So remember, it's 44% of our fuel mass limit main value. Let's just head back across to that for a second. We can see that that's 137 milligrams. Okay, what we'll do is we'll have a look now at our dyno screen, and what we're looking at is the torque being registered. So it's moving around a little bit. We can see that we're sitting around about 180, 185 Newton meters. So what I'm going to do now is I'm going to adjust that percentage. Let's take it from 44 up to 55%, and we'll watch what happens to our torque. So we can see that that went from 185 Newton meters up to about 225, 230. Okay, so we can affect the amount of torque that the engine is producing based solely on the fuel being delivered. So again, this just represents that we aren't using the throttle body which we would with a gasoline engine in order to modulate the airflow into the engine and control power. Instead, what we're doing is modulating the fuel delivery to have that effect. So that's why we don't need a throttle body. Now the other effect of this though, as I mentioned earlier, is as we inject more fuel, this affects our combustion temperature and in turn our exhaust gas temperature. So let's just have a look at this here. At the moment on our laptop screen, what we've got here is our engine speed at the top. We've got our exhaust lambda as our next plot. We've got our fuel mass being delivered, and then at the bottom we've got our exhaust temperature. So this is a really important point. We can't measure the temperature of the combustion chamber directly, but what we can measure is the exhaust gas temperature. So we can see that over a good chunk of this log here, before I made any changes, we're sitting at a lambda of about 1.47, 1.5. It's obviously moving around slightly, and we can see at the same point that our exhaust gas temperature is stabilized at about 495 degrees centigrade. At the point where I make the change to our fuel mass, we can see that indicated by a jump in our fuel mass being delivered. At exactly the same time, we see that representing a drop in our exhaust lambda. We've gone from 1.475 down to 1.30, and what we see here is our exhaust gas temperature begins to climb. So at the point where I backed off the throttle there, we hadn't quite reached equilibrium, and you can see that we've gone all the way up to 562 degrees centigrade. So those are the interactions that we need to be really careful of when we are adjusting our fuel delivery. We want to make sure that we're monitoring that exhaust gas temperature and that it isn't going to end up dangerous to the engine. Okay, so what we'll do now is have another demonstration. This time we're going to see how our injection timing affects our torque. So if we just jump into my laptop screen for a moment, we'll just get ourselves up and running here again. So this is our fuel timing primary table. So this is where we're defining the timing for our main injection pulse. And what we're going to do is come up here to around about 3000 RPM, and again we'll just have a look at the effect of our timing value. So let's get our engine up and running at 3000 RPM. And we'll see what that does to our torque. So essentially we're looking at exactly the same gauge that we looked at just before. We'll just get our RPM up a little bit further. Okay, so we're operating now at 50 milligrams of fuel delivery, 3000 RPM. And again, if we look over at our dyno, we can see that we're sitting at about 135, just moved around a little bit, let's say 150 Newton meters of torque. Okay, what I'm going to do now, the moment we're beginning our injection event 15 degrees before top dead center, what I'll do is I'll just highlight all of these so that we are making a change to all of them together. So we're still sitting at about 145, 150 Newton meters. I'm going to retard the timing. I'm going to go back to 0. we'll see that our torque drops away. We drop back to about 110 Newton meters. So we've seen that's offered a reduction in our engine torque. So let's advance our timing a little bit. We'll start our injection event now 5 degrees before top dead center. I'll press enter. We can see that takes us back to, over the time everything settles, around about 120 to 125 Newton meters. Let's try 10 degrees. I'll press enter and that change will be locked in. And we can see that we're back up to about 140 Newton meters. So the process there of optimizing our injection timing is really quite similar to the process of optimizing our ignition timing in a gasoline engine. What we're doing is moving that injection event around in order to make sure that we're getting peak cylinder pressure occurring in the correct point in the cylinder. The problem with this, as I've mentioned though, is that if we advance the timing, we start our injection pulse too early in the engine cycle, this can result in damage to the engine. So this is something we do need to really tread carefully with. We want to be really careful with that. We also find that if we just jump back into my laptop software again, we can see that the general trend that we've got here as we move from low RPM to high RPM, we can see that we tend to advance that injection timing. We want to start the injection timing event a little bit earlier in the engine cycle, so we can see that particularly at 4,500 RPM with 90 to 100 milligrams of fuel delivery, we're starting our injection event around about 27 degrees of crankshaft rotation before we reach top dead center. And the reason for this is that as our engine RPM increases, there's less time available for the combustion process to occur. So exactly the same again, if we draw a bit of a likeness here to gasoline engine tuning, we have that same trend with our ignition timing. As we increase our engine RPM, the general trend there is that we advance the ignition timing as well. Okay, so what we want to do now as well is just have a look at the smoke production from our engine. So really, if we want to be environmentally friendly here and produce an engine that is producing good power and torque, we also want to be mindful of running the engine so rich that it does produce smoke output. We'll find also that a lot of the race classes, particularly circuit racing classes where diesel engines are now being brought in, there is actually a smoke limit. So basically if the exhaust is seen to be producing smoke, then often the engine, that car won't be allowed to compete. So it's something we do need to be mindful of. So I just want to explain exactly how that works. Let's head back across to my laptop screen for a moment. So I've already talked about here our fuel mass limit main. Remember, this was the maximum amount of fuel, really simply here relative to our engine RPM. So this is the maximum amount of fuel that can be delivered into the engine. Then on top of that, we have our fuel mass nominal table. So this is the percentage of that maximum amount of fuel that can be injected, and remember, this is relative to our throttle position. So a value of 100% here means that we're injecting the fuel mass limit main value. However, there are some other tables that work on top of this. So we'll head across to our smoke limit table here, and what we've got here is another table. Let's just have a look at that graphically. So this is a three-dimensional table relative to engine RPM and our engine load. So we've got a value here that MoTeC defined as engine charge limited. So what this does is allows us to limit the maximum amount of fuel that will be delivered into the engine relative to engine RPM and our current engine load. So this is really important because if you remember, if we head back to our fuel mass table and we'll go back to our fuel mass nominal table, so this is relative to throttle position. But our engine is turbocharged, so we can go to 2000 RPM and wide open throttle, and let's have a look at that value for a moment. We have a value of 81.5%. But we can be at 2000 RPM, and when we initially get to 2000 RPM, we're probably going to have little to no boost pressure. But if we stay at 2000 RPM, obviously that turbocharger is going to come on boost. As it comes on boost, the boost pressure increases, the mass airflow into the engine also understandably increases. So what we need is a way of regulating the fuel delivery relative to the mass airflow, and that's what we can do with our smoke limit table here. We can at lower load values, which we can see down here, you can see that at lower engine loads we are limiting the maximum amount of fuel that will be delivered into the engine. Okay, so what we'll do now is we'll just do a quick demonstration here, and what I'm going to do is purposely run the engine very, very rich, certainly not something I'd recommend. We're going to do this at 2000 RPM and wide open throttle, and we're going to switch to an external camera that will allow you to see exactly what's coming out the tailpipe. So let me just get our engine running at 2000 RPM before we actually do this test. Okay, and I'm going to just go to our fuel mass table. Okay, so I'm just going to go to full throttle now, and hopefully what you're going to be able to see is some black smoke coming out the exhaust. And at the moment our exhaust lambda was sitting at around about 0.9 briefly there, so I haven't unfortunately been able to see that. Hopefully that test has been useful and actually demonstrated it, otherwise it's going to be a pretty awkward demonstration. But let's just jump back into our laptop software and see what was going on there. Okay, so we can see we're at 2000 RPM here, and we can see that our lambda here, as I've gone to full throttle, we've gone very, very rich. We've gone as rich as about 0.9, and remember I said that generally our rich limit is around about 1.1 at the point where we're going to end up getting smoke. So we're running very, very rich here, and you can also see the result of this on our exhaust gas temperature, particularly even though that was a really short test, we ended up getting up to 600 degrees centigrade, and we are still rising. So again, this is an aspect we do need to be very mindful of. Okay, so let's just go back over that. There's been a lot of information that I've presented there, so I want to just go back over it and summarize. So first of all, the most important thing, if we want to make more power from a diesel engine, which obviously that's what we're all predominantly interested in, we're going to need to add more fuel, and preferably we also want to add more air and fuel. So the increase in the airflow comes from increasing the boost pressure in our turbocharger, or alternatively swapping also to a larger turbo. Of course, the diesel engine works the same way as a gasoline engine in terms of anything we do to reduce restriction on the engine on the inlet side in terms of the airflow into the engine, as well as the exhaust system on the exhaust side of the engine will also improve airflow and engine efficiency. Okay, so once we've done this though, we want to increase the fuel delivery, so that is going to require a larger pulse width from our injector. Remember that this is going to, if we do nothing else, if we just increase the injection pulse width, this is going to put our 50% burn point later in the engine cycle. We know that this is not ideal for torque, and it also can result in smoke, and it also can result in emissions. So we can combat this by advancing our injection timing. Now this is effective to a degree, but as I've already mentioned, it is potentially dangerous if we advance our injection timing too far. So we want to be very mindful of this, and I certainly would be very, very careful and warn against making wholesale changes to the injection timing. So our solution really there is to increase our fuel pressure, because this means that we can provide more fuel mass with a shorter injection pulse width. Now obviously there is a limit to how far we can go here. Normally in a factory diesel pump, there is the ability to raise the pressure slightly above what the factory settings would dictate. There's also a spill valve on the mechanical pump which acts as a limiting device for our maximum pressure, so we can't go on indefinitely increasing the fuel pressure. In the aftermarket for popular diesel engines, there are larger fuel pumps that can provide more fuel volume and more fuel pressure, so that's another option we can look at if there are products for the particular engine you are fitting. Tuning. Now ideally what we want to do though is fit larger injectors. So this fixes a lot of our problems there. It allows more fuel to be injected for a given fuel pressure and pulse width, so that fixes our problem with our expanding fuel pulse width into the engine. It allows us to retain the same injection timing or very close to it. Unfortunately, there can be limited options in the aftermarket diesel world for some applications. So particularly if you're dealing with an engine that isn't popular for modification, then this can present some issues. What we find is that it is quite common in the diesel tuning world to provide aftermarket nozzles that fit onto the end of the fuel injectors that increase the flow out of the existing injector. So that's going to give us the potential of, in some cases, 30 to 50% more injector flow without actually replacing the injector itself. Okay, one more thing that I want to talk about here, and this relates to our boost control. Again, this is something that's really easy to overlook. The amount of boost that we end up with actually is also affected by the lambda that we end up running. So particularly if we take a factory diesel engine and we increase the fuel delivery to richen the lambda, richen the air-fuel ratio, as a result what this does is it produces more heat in the exhaust. This provides more energy to drive the turbocharger, so we can find that even while we haven't made any changes to the turbocharger boost itself, we've left that untouched, we can find that the actual boost pressure may rise. So this can be an iterative process of adjusting our fuel delivery and then having to go back and adjust our boost control settings as well. And particularly this becomes even more problematic if we are running a VNT turbocharger, because there is a lot more going on there. The VNT turbos are often controlled by a stepper motor, so we're going to be going through an iterative process of adjusting our fuel delivery, adjusting our boost pressure, adjusting our fuel delivery, etc., until we get the boost pressure that we want to be running and our target lambda.
That was just a taste of what we put on every week for our HPA Gold members. Our Gold members are able to watch these live and ask questions and get answers while we're presenting. After the webinars have been hosted live, they're added into our webinar archive where our Gold members can re-watch them at their leisure. We've currently got over 240 hours of existing webinar content covering topics on engine building, engine tuning and wiring. This is one of the fastest ways to expand your knowledge on a wide range of topics, as well as to stay up to date with the latest tools, trends and techniques in the performance industry. Our Gold members also get access to our private members-only forum, which is the best place to get fast answers to your specific questions. Gold membership can be purchased for just $19 per month. However, you'll also receive 3 months of free access with the purchase of any of our courses. Click the link in the description to learn more.